the explanation by looking at this kind of strange diagram that I've drawn here. This guy here is a node in some circuit, and the funny green stuff is what we would call the rest of the circuit. And the thing is, for Kirchhoff's current law, we don't even care what the rest of the circuit is. What we're going to, in order to state it, basically the way it would work for this particular picture, one way of stating it is I1 plus I2 plus I3 plus I4 plus I5 is equal to 0. In words, the sum of all the currents entering a node, this is our node, is equal to 0. Now, some of you may look at this and say, wait, how can you have the sum of all currents entering the node be 0? Well, it means that some of these currents are going to be negative, so that the way we've drawn the arrows won't show how all of the currents are going to flow. Some of the currents will be flowing out of the node. Otherwise, I can't have the sum of currents being 0. And conceptually, what this means is that the current, which again is flowing charge, into the node is the same as the current out, which means that as much charge flows in as flows out. So I don't have charge accumulating at a node. That's basically what we're saying with KCL. Another way of writing KCL, let's do this one in magenta. Suppose some of the currents are going the opposite direction. So for example, I3, we'll assume I4 is still going the same direction, but I5 changes direction. So a way I can write KCL for this one is I1 plus I2 plus I4 is equal to I3 plus I5. In words, the sum of the currents entering the node is equal to the sum of the currents leaving the node. Either you can convince yourself that these are mathematically correct or mathematically identical. I tend to prefer the second statement just because it intuitively makes sense to me that the current flowing in has to be the same, or the total current flowing in has to be the same as the total current leaving the node. So with that as an introduction, let's actually do an example. So what I've drawn here is a circuit that represents 4 light bulbs connected in such a way that they'll all be lit at the same time. And just for your edification, this first light bulb is a 100-watt light bulb. I then have 2 60-watt light bulbs and one 40-watt light bulb. Okay, and you can go back and look at the video on Ohm's law to convince yourself that given the voltage we have and the values for the resistances which model the light bulbs, that we do indeed have 100-watt, 60-watt, and 40-watt bulbs. Okay, so what I want to do is find out the total current coming out of this source. Okay, I want to know this current because perhaps I want to know how much current it's going to take to light these light bulbs. A practical application of that is if you put too many light bulbs on one circuit, you'll trip a breaker, which means that you won't be able to turn on all your lights at once. So I'll denote the current coming out of the source as I, and I'll denote the current going through the 100-watt bulb as I1, the current going through the first 60-watt bulb as I2, current going through the third 60-watt bulb as I3, and the current going through the 40-watt bulb. Did I say third 60-watt bulb? That should be second 60-watt bulb. And then the current going through the 40-watt bulb is I4. Okay, and I want to find out what the total current is. So I can write down KCL, which says that the current flowing into the node is equal to I1 plus I2 plus I3 plus I4, the currents flowing out of the node. Now, at this point, I'd like to take a bit of a digression because I've discovered that this particular point can be rather confusing, and it's one of the big misconceptions that students have. Sometimes students will think that the node would be wherever I join wires, and my previous picture to introduce KCL might reinforce that misconception. But a node is anywhere I can get to by following a wire. So as I draw here, I'm actually drawing an outline, if you will, or a green line that encloses all of one node. Okay, so this part that I've drawn in green is all one node. And the way I can tell that is I can get from any point, say this point here, over to some other point, say this point here, by just following a wire. There are no components on my path from here to here. And if you look at the way I've drawn this green outline, there are no components on the path between any part of the wire in the green outline to any other part of the wire in the green outline. So this green thing is a node. And because it's a node, I can apply Kirchhoff's current law to it, which gives me the equation that we have. Similarly, the part that I'm outlining in red is also all one node, using the exact same logic. Okay, so everything outlined in red is one node. Now, this is important to me because the voltage source is going to make sure that the voltage between the green node and the red node is 120 volts. So what that means is that the voltage across the 144 ohm resistor is 120 volts. The voltage across the 240 ohm resistors are both, those voltages are both 120 volts. In other words, the voltages across all the resistors are 120 volts. Again, that's because the voltage between the two nodes is exactly 120 volts. Since I now know these voltages, I've got a voltage, here we'll start this in an even worse color. I've got a voltage and I've got a resistance. If I know the voltage across this resistor and I know its resistance, I can use Ohm's law to get its current. So I1 will be 120 volts over 144 ohms, which turns out to be 0.83 amps. Similarly, let's see, what's a beautiful color? I2 will be 120 volts over 240 ohms, which is 0.5 amps. I3 will be the same, 120 volts over 240 ohms, which is 0.5 amps. And I4 will be 120 volts over 360 ohms, which is 0.33 amps. Okay, so if I plug all of these numbers in and solve for I get that I is equal to 0.83 amps from I1 plus 0.5 amps plus 0.5 amps plus 0.33 amps, which I will try to do this math in my head, which means I'll probably get it wrong, is 2.16 amps. Okay, so what this says is that the voltage source, in order to keep 120 volts across each of the light bulbs, we'll have to put out a total of 2.16 amps. Okay, so the last point I want to make is you'll notice that the currents leaving the node, I1, I2, I3, and I4, you'll notice that these currents are not all the same. This is a common misconception, that if I have if I have a current coming out of a source and I have a bunch of resistors that current splits into, that it splits into equal currents for each resistor, and that's not true. The current will depend on the value of the resistor. So that's why I1 is the largest, because the resistance, 144 ohms, is the smallest. That's why I4 is the smallest, because it has the largest resistance. So that concludes our discussion, our presentation of Kirchhoff's current law. I hope you enjoyed it.